So hello everyone, welcome to our this week Ruggers Efficient AI seminar. And today we're very glad to have the Professor Vidya Chhabria from the Arizona State University to give us this talk, a very interesting topic, the role of the AI in physical design. And Vidya is currently assistant professor in the School of the Electrical, Computer, and Energy Engineering at Arizona State University, and she received a PhD from the University of Minnesota. And her research interests lie in computer-aided design for VSI systems and primarily revolve around using machine learning for physical design, optimizations, and analysis algorithms. She has received the ICCAD Best Paper Award, that's a very prestigious award, and the University of Minnesota Best Dissertation Award in Mathematics, Physical Science, and Engineering category. So now let's welcome Vidya to give us this talk.
Hi, everyone. Thank you, Bo, for the introduction. And I'm very excited to be here virtually and present some of the research that I've done with all of you today. So thank you for the invitation, Bo. Um, so today the talk is going to be about the role of AI in physical design. Um, just for background, this is what I'm going to do today. I'm going to talk about a little bit about what EDA is, electronic design automation, what physical design is, and then go into three different applications of AI and EDA, and then I'll conclude. So our research in my group is in the area of EDA, or electronic design automation, which is an area that builds algorithms or softwares to design chips. For decades now, chips have been growing in complexity. We started at having tens of transistors on the chip to today having millions, if not billions of transistors on a chip, to having having almost trillion transistors actually on the chip. And while Moore's law has really been responsible for the scaling and this growth in complexity, an unsung hero has been electronic design automation tools. It has enabled us to move away from the manual design of circuits and layouts by hand to automatically designing, optimizing, and analyzing large scale circuits. It's been one of the key reasons we see all these growing trajectories here. And I like to use this cartoon picture to demonstrate the role EDA has played all these years. EDA itself has made the life of Moore's Law and an IC designer easier. In this cartoon, EDA itself is represented by this hand truck, along with Moore's Law together has allowed software to grow in complexity while being able to sustain the compute and energy demands of several different high performance applications. However, while we see these growing trajectory here, everything has not been that simple. In the recent past, about a decade or 15 years ago, with the end of Dennard scaling, things have become much more harder for Moore's law to sustain. Yes, the number of transistors on the chip is still growing exponentially, as you can see by this orange trajectory here. The number of useful transistors on the chip, or the number of transistors that actually contribute to an improvement in power, performance area, etc., have not been growing at the same rate, showing this significant gap, which is shown by the slowdown in the processor single thread frequency, or the single thread or the frequency of today's processors. Further, to make things more challenging, the advent of AI and high compute demanding tasks such as AI actually have made things a lot more challenging. For example, the complexity of machine learning models has been growing exponentially towards this path for better accuracy. In this picture here, it shows that since 2012, that was the year, if you remember, AlexaNet had its success on the ImageNet dataset. The amount of compute that's required in training these largest AI models has been increasing exponentially with a 3.4-month doubling time. Since 2012, this metric has grown 300,000 times. So now bringing in that previous picture from the last slide here and aligning the time axis, even though the y-axis is not the same here, my message here is very clear, which is that previously Moore's law had a 2-year doubling time, which was assisting hardware to keep pace with these software or these growing demands from software. However, there's not only been a slowdown in Moore's law that's shown by this design capability gap, there's also been a boom in AI. So if you thought this gap due to the design capability gap was bad, just look at this gap that AI has created. We need systems or hardware that are far beyond today's capabilities in order to sustain the demands of today's AI applications. In fact, it's important to note here that this slide ends 2 years ago. It's about 2012 over here. I mean, it's about 2022, and that hasn't even considered the advent of large language models and all your chat GPTs into this picture. So this slide sort of brings me to the big picture goal of the research that we do here at ASU. And the idea is, can we develop significantly better EDA tools that can both keep Moore's law afloat, that means bridge this design capability gap, and that can also help bridge this demand that AI has created, or basically any compute intensive application from software has actually created. So that's sort of the big picture goal of the research that we do here in my group at ASU. So for today's talk, I'll be talking about the role of how AI can actually help EDA tools that can design better significantly, that can help AI can help design these significantly better EDA tools. And I'll talk about it in the context of physical design. When I think about EDA, I typically think about these three things. I think about algorithms. So algorithms that can help us automate things. Push a button, a chip is ready, for example. So it's automation. Those would include productivity improvements and lowering the barriers to entry. That's EDA has automation. The other thing I think about is optimization. A lot of EDA algorithms are about run optimization algorithms under the hood, which are trying to improve the QOR, either PPA of the chip. And the third thing that I think about here is analysis. Analysis tools are EDA tools that can check the correctness of a design, timing analysis, power analysis, um, temperature analysis, IR drop analysis as examples. So when I think about EDA, I typically think about these three tasks here. There's also another thing which I'll talk about, which is this bonus question, which is where about benchmark generation. But let me get to that in a little bit. If you look at these three tasks, automation, optimization, and analysis, all the algorithms that perform these three different things have several challenges with EDA. The reason we see those large gaps or design capability gaps or AI or hardware not being able to keep pace with software is because EDA tools, one of the reasons is because EDA tools are computationally very expensive. As hardware grows in complexity, most EDA tools are NP complete, solve NP complete algorithms, or actually addressing or actually developing NP-complete algorithms that have polynomial time complexity in n, where n is the number of transistors. And if you have polynomial time complexity in n, with n being the number of transistors, those EDA tools do not scale. When you have transistors that go from million to trillion transistors, the amount of time it takes to perform the same task, whether it can be timing analysis, power analysis, it increases significantly. And it's created problems such as larger time to market, larger runtime of EDA tools, and basically increase the amount of time it takes for a chip to go from concept to tape out. The second thing that I want to say is that EDA tools are mostly heuristic based. They often trade off speed for accuracy. So if you want to improve the runtime of an EDA tool, you typically sacrifice accuracy, or if you want to improve the accuracy, then you have to sacrifice runtime, and you have large amounts of runtimes. That's a problem. It also requires significant amount of manual intervention to perhaps set knobs. There are several number of knobs in EDA tools. Set this parameter to be this value, set this parameter to be this value. And that requires significant amount of manual intervention from an expert chip designer to set those knobs in EDA tools to get the layout or to get the chip that you really want to tape out. So these challenges are one of the reasons why EDA tools today, why we hear questions such as, has EDA failed to keep up with Moore's law? And as an EDA engineer or an EDA researcher, I find it very I feel ashamed to see such questions, right? So for this talk, I'm going to focus about how we address these different challenges. In particular, I'm going to focus on three different things. I'm going to focus on automation and productivity improvements. Can AI help improve the productivity of today's chip designers? That's the first thing I'm going to talk about. Second thing I'm going to talk about is, can AI help us speed up different analysis algorithms, right? The third thing I'm going to talk about is this notion of generation, because when we talk about AI and chip design, there's always a question of, where did the data come from? So can AI actually help us generate data? This task about optimization, I will not cover in the interest of time, but we do have a lot of work in how AI can help optimize power grids, how AI can help optimize timing within the chip and things like that. But for the interest of time, I'm going to skip out of this. So my argument here is that there have been goals such as can we reach this idea of 24 hours, no human in the loop, no performance power area loss? And my idea here is that AI inside EDA tools, AI outside EDA tools are basically leveraging AI to help accelerate EDA tools can help us get closer to these goals, such as 24 hours, no human in loop, no power performance area loss. The scope of this talk is completely going to be in physical design. And this on the picture here on the left shows what physical design is. The goal is to take Verilog or an RTL description all the way down to layout, automatic place and route. Most of the examples that I give here of AI-enabled EDA are going to be within the scope of this talk. Timing analysis, IR drop analysis, etc. Okay, so that sets up the context for what I want to talk about. And I'll be talking about these three examples now. The first example is automation. And I'll talk about a recent work that we did, which developed a chatbot for an EDA tool, because most times EDA tools are very difficult uh, uh, for a user who doesn't have experience to use. For instance, when I give a new EDA tool, if I give my student an EDA tool of, let's say, Innovus, and I say, hey, this is Cadence's Innovus, can you try to implement this layout, or can you try to implement this design using this tool? It's very, very challenging for a student who's not been able to do it before to do it. So it helps automation, or it helps sort of ramp up a newcomer. And I'll talk about this chatbot in the next few slides. So if you think about applications of generative AI, or let's say large language models, in EDA or in chip design, there have already been several works in the past that are attempting to incorporate LLMs into chip design field. And here I list a few notable examples. What you can see here is that most of these examples are about using LLMs to generate RTL or to solve synthesis problems or front-end problems in chip design. And the reason for this is that because RTL languages are open languages. If you think about Verilog, it's a, sort of an open language. I can write Verilog, you can write Verilog. There's no restriction by licenses, making it easier to prepare data for LLM related work. But on the contrary, if you think about physical design tasks, it's significantly more challenging. Commercial physical design tools are limited by several factors, such as end user license agreements, commercial PDKs there, which you have to sign very, very strict non-disclosure agreements. The EDA tools do not give us open source APIs. They're all closed source APIs. We do not know what's happening under the hood. I cannot take EDA tool Tickle and put that into ChatGPT, for example. And these are several barriers that have been restricting the use of AI or been restricting the use of applying large language models to physical design. However, open source EDA and open source PDKs that have emerged in the past few years have provided a path towards addressing this. In particular, as an example, there's a tool known as OpenRoad, which is an open source RTL to GDS toolchain that takes Verilog and gets out GDS2. This toolchain was developed as a part of a DARPA IDEA program that came about 5 years ago. And I've contributed a lot towards this tool during my PhD. And the idea was, given that we have this open source tool, can we now apply large language models or develop a chatbot for how we can use this tool to lower the barriers of entry for anyone else who wants to use these tools? While this example is going to be only tailored to OpenRoad, the concepts can be applied to any other tool within, let's say, using a commercial tool, but as long as you're not um, uh, uh, violating end user license agreements of the tool. So if you think about what has happened in the past, or what are the prior works that have tried to incorporate large language models into physical design, and there are two that come to mind. The first is this paper called as Chat EDA from the Chinese University of Hong Kong that was presented last year at MLCAD, and it uses a Llama 2-based model to perform to perform various physical design flow tasks, and it performs tasks planning, and then there's a translator that takes those tasks and then generates the scripts to perform each of these tasks. The work generates scripts for open source physical design tools again, such as OpenRoad. The second one that really comes to mind is this one from ChipNemo from NVIDIA, which uses a Llama 2-based model to do several different design tasks, to several different design tasks, and one of it is generating scripts for physical design STA tools. The challenge here is that there are 24 billion models of training tokens that are used, right? 24 billion models of training times that are used, massive GPU training times, all with proprietary data, which makes it very inaccessible to small research groups and academia in particular. And it's all proprietary data, so we don't have access to the model, we don't have access to data, it's all within NVIDIA. Despite the effort these two papers have put into physical design LLM research, there are several limitations, of course, as you can see here. Very, very inaccessible proprietary tools, large data available only within a large design company such as NVIDIA. This paper here on the left was a very simple first mover paper that tried to apply large language models to various physical design tasks. But it required translation of these scripts. For instance, it performed only task planning, and there was a need for a translator to actually generate scripts to do different physical design tasks, which was one of the bottlenecks. So recently, we worked on this to overcome some of these challenges and to develop a large language model, open source large language model for EDA tools. We released this data set known as EDA Corpus, which is an open source data set for physical design tool scripts and general question answering. And it was released earlier this year in May and made publicly accessible. It includes about 1,000 data points of prompt script pairs. Prompts include generate code, set the rotation of an instance in the database to some value, prompts such as this, with the corresponding pair of its script that's shown here. This is OpenRoad Python script to do that task within OpenRoad. And it also includes about 600 different pairs of question and answers about OpenRoad. And it could be questions such as, what is PDNGen? Why is the PDN module in OpenRoad? How does it do? What is its contribution to the floor planning step? How do you generate the power grid? How do you perform placement? How do you perform routing? And several different questions and answers pairs that are available. So we released this large data set. And the way we curated this data set is essentially through a lot of manual work. We had students mine the OpenRoad project GitHub repository, mine issues, mine discussions, mine README files, and create EDA corpus for the prompt. This was for the question answers. And for the prompt and script, we had different students contribute different prompts and write scripts for that in OpenRoad. And we created that about 1,000 such data points from 6 to 7 different students who kept writing prompts and scripts and prompt and scripts and curated that to build this EDA corpus. Using that corpus, we went ahead to create a model, which is known as OpenRoad Assistant, or it's a chatbot for performing physical design tasks using OpenRoad. And the key contributions for that are listed here. It's an open source EDA tool with an open source model and an open source data set. Second, it's a developed chatbot for directly generating EDA tool scripts within OpenRoad. So this script, once you give it a prompt, the script is generated that can perfectly run within OpenRoad directly. It doesn't need a translator like how Chat EDA needed. And it also can answer different questions that are related to OpenRoad or physical design in general, such as, oh, what is the significance of this argument in this command? Or why do we need floor planning? Why do we need placement, etc.? And the last one is that this work also proposed a new large language model training method for training this model with very limited number of data points, because our EDA corpus is not very big if you think about it. I'm sorry. EDA corpus is not very big if you think about it. It's about 1,600 data points, but we're training a large language model of a Llama 3 8 billion model parameter. So how can you train it with such a few data points to perform the task that you really need to? So we did come up with a new LLM training method for working with this domain-specific EDA data. So in this work, we use the LoRa, QLoRa, which stands for Quantized Low Rank Adaptation. And it's a method to train additional weights to a model and attach them to the original model. And this approach can significantly lower the training cost, since we do not need to fine-tune the entire model's weights. I will now use a diagram to illustrate our training process. So in OpenRoad Assistant Flow, we use EDA corpus dataset and we filter out the unique pairs of EDA data, unique data pairs. What does that mean? That basically means that we ensure all the data points are distinct from each other, and we separate it out into training and test set to ensure that there are no replications of the training data in the test set. Once we've done that, in addition to the EDA corpus dataset, we also have a RAG database, and I'll talk about what what the contents of the RAG database are. RAG stands for Retrieval Augmented Generation. So after gathering these two data sets, we use a raft-like technique to compute a new data set. And what raft stands for is Retrieval Augmented Fine-Tuning. And this new data set has the same prompt and answer format, but for each prompt, it's enriched by providing context from the RAG database. We automate this process by using a retrieval model to select the top 3 contexts from the RAG database. We concatenate the top 3 contexts of the RAG database with the user prompt that comes in, and that context plus prompt is what serves as our input to the raft dataset with the corresponding label from the EDA corpus as the training set. So this RAF dataset is used to then train a Llama 3 8 billion model. And this is basically fine-tuning the Llama 3 8 billion model to perform different tasks such as question and answering and script generation for open road. For the question and answering adapter, then we have 2 different adapters, one for script generation and one for question and answering. For the question and answering adapter, we also use an open source data set to perform instruction fine-tuning, which means we take Llama 3, take this instruction data set, perform fine-tuning. This instruction data set has nothing to do with open road, but it's just a general question and answer format to make the Llama 3 model understand that we're trying to train it as a very specific chatbot in the form of Q&A. And we also have another additional training step here for the question and answering, where we not only use the automated response from the retrieval model to construct the RAT data set, but we also handpick some contexts, like manually select the context from the RAT database, paraphrase some of those contexts, and then put that into the RAFT data set. So this is an entire flow of our open road assistant training. And this slide here shows some of the details of our RAG database. For the script generation, the RAG is built using 2 types of contexts. The first is a list of all possible APIs that are available in open road. This could be APIs such as, hey, is this a buffer? Can you flip the cell? Or can you perform timing analysis? Can you perform power analysis? What are the different commands to perform those? So that there's an API list. And the other is what's a template list. Typically, when you're performing physical design, there is a set of templates that you would use to run these scripts in your EDA tool. If I have to run the global router, I need to first, or if I have to run the detailed router, I first need to set certain parameters for the detailed router. Then I need to run detailed routing, etc., etc. I need to set the number of metal layers. All of those templates are available within our RAG database. So we have a list of all the APIs, and we have a list of different templates to perform various different tasks in open road. For the Q&A adapter, the RAG dataset is built from README files, and we first gather all the README files and then crop them into feasible sizes to actually construct this RAG database for Q&A. So we have 2 databases, RAG database for the script generation, RAG database for question and answering. For the script generation, we use an API list and the templates of codes. And for the Q&A database, we use a RAG database that consists of different README files. So that's about training. Once the model training is complete, this is what it looks like during inference. We pass a prompt to the model. The prompt will first go through the retriever model. The retriever model will collect the top 3 contexts from the RAG database. It will concatenate that context with the question, and that goes into Open Road Assistant, and Open Road Assistant will generate the answer or the script. So an example here of using a script adapter is shown. The script generation demo shows here how we can ask Open Road to generate scripts for querying different data within Open Road database. So it says get every pin from the design and put it in a Python list. And then our Open Road model will generate this code, which can get all the pins in the design, and it can append that into a list in Python, and it returns that. And this piece of code will run within Open Road. If you can copy this, paste it within Open Road, it does exactly that. So to evaluate the performance of our Q&A adapter, we use BERT score and BART score, which is sort of BERT score evaluates the semantic similarity between the data that's in the corpus and the data that is actually generated. And BART score conceptualizes the evaluation of the generated text and the problem itself. It looks for fluency, etc. For script generation, we use two metrics, parset1 and parset3, or parset-k, essentially, which is a very commonly used metric for script generation in the AI world. And this slide here shows the performance of Open Road Assistant for script generation, and it compares it to whether various other baseline models. And for details on the ablation study on what these exact baseline models are, I encourage you to take a look at our paper. If you can look at the result, we have two kinds of data. We have two kinds. There's something called as partially correct, and there's something called as correct. Partially correct is basically when we have less than one change in line of code that's needed. We created this class called as partially correct because sometimes the script that is generated requires only one change in the line of code, and that is very, very trivial to do. I can show some examples if there's interest, but we had these three different classes. There's wrong, there's partially correct, and correct. And you can see that our model outperformed various different baselines that we had, and I encourage you to take a look at the paper. Similarly, even on the question and answering side, for the BERT and BART score, we have precision recall and F1 scores for these metrics, and Open Road Assistant outperformed several different other baselines. To conclude this part of this presentation on automation, I'm going to say that this is the first LLM for native physical design tools, scripting, and question and answering. We adopted the RAF technique to reduce hallucinations by concatenating the context from the retriever model and the prompt, and it outperformed various baselines. All of this is open source available. These are the different QR codes for our Open Road Assistant scripts. Our model is on Hugging Face, and our data set is also on GitHub. So that's about the first part of my talk. I'm going to pause here to see if there are any questions about this, and I'm happy to take before I move into the next slide. If not, I can move ahead. Are there any questions before I move ahead?
Yeah, actually, I have some questions, but I think you can first move forward. Yeah.
Okay, sure, Bo. Okay, so that was an example about using AI to perform automation. And that's sort of to lower the barriers of entry for a non-expert user, to make their life easier by creating this chatbot to help them use the EDA tool. Next, I'm going to talk about an example about analysis, about how AI can help different analysis. Now, if you think about the example that I'm going to use here is the example of thermal and power delivery network analysis. So I'll first set it up with some context. So power delivery network analysis itself, or PDN analysis, if you think about it, the goal of a power delivery network is to take voltage from the outside of the chip and bring it down to every single transistor on the chip. Now, PDN analysis, so that's the goal of the power grid, right? So as voltage goes from the outside of the chip, as it goes towards the bumps, it comes through the RDL layers, down through various different metal layers, and then comes down to every single transistor on the chip that's shown here. So this is a power grid, consists of multiple metal layers. You can model this power grid since it's as the circuit that's shown over here. The bump itself is a voltage source because it's bringing voltage from the outside of the world into inside the chip. These metal lines can be modeled as resistors and capacitances that are shown here. And the transistors that are below, or the logic cells that switch, whenever they switch, they draw current. So those can be modeled as current sources that are shown here. So the goal of PDN analysis is the goal of the power grid is to bring voltage from the outside of the chip down to every single transistor without significant losses. What do I mean by without significant losses? I want to ensure that the voltage at this point near every standard cell is almost the same as what it was outside, which means you want to have minimal voltage drop through the circuit or minimal IR drop through the circuit. And you also want to ensure that this circuit meets something called as electromigration constraints, where the current density through each of these wires is less than certain standard potential that is less than certain limit that's available. So those are the two constraints. Now, to check whether your power grid is good or not, that's when you perform power delivery network analysis, PDN analysis, and you're essentially solving this entire circuit to compute the voltages at the logic gates that are below here. So you're solving this. Now, if you think about this, you can solve this using SPICE. You can solve this it's just an RLC circuit. I mean, it's a RC circuit with voltage sources and current sources, right? So you can solve this using SPICE. While you can think that this is solvable using SPICE, the challenge here is that it's a very computationally expensive problem to solve. The number of nodes in this system in today's real chips is in the order of billion nodes, which means like imagine writing a SPICE netlist which has over a billion lines of code and trying to run that using SPICE. It's going to take forever for you to get a result or figure out what the voltage is. So for sign off, what you typically want to ensure is that the voltage at every cell is larger than this particular limit, but finding out that voltage is very difficult. Even if you think about it in static state, which means when you don't have capacitors, you're solving this system of linear equations of the form GV is equal to J. This is what SPICE does under the hood. And this equation has billions of variables, which means the matrix size of G is about a billion cross billion, and it is very expensive to solve. It takes hours and hours of runtime on a simple test case that I, in academia, have access to. It's a RISC-V core. It takes hours and hours of runtimes to even solve for static IR drop, basically to solve the circuit without capacitors. Another equally important analysis is thermal analysis. And if you think about thermal analysis, on-chip thermal analysis, you're solving this finite different method-based heat flow equation that's shown here. Think of it as you're solving a second order partial differential equation that's shown here, where you're trying to compute T. Even in both these algorithms, power delivery network analysis and thermal analysis, are computationally expensive, but they both map onto very similar algorithms under the hood, where in steady state, you're solving a large system of linear equations of the form GV is equal to J or GT is equal to P. Both of them are computationally very expensive with hours of runtime on industry scale design. And the goal over here is to use AI to speed up this task. So as an example, I'm going to take thermal analysis. And if you think about the transient thermal analysis problem, conventionally, it's going to be solved by solving this equation, which means you're going to perform numerical integration on this equation to actually get the values of temperature. But here, if you think about it, conventionally, you're solving numerical integration, which is why it's computationally expensive. But if you try to think about it in the terms of fundamentally, what is the input, what is the output? The input is time varying distributions of power across the chip, and the output is the corresponding time varying distributions of temperature across the chip. You'll notice that both of these maps are correlated, but they're not identical. A region which has high power also tends to have high temperature. So what we've done is we've mapped the thermal analysis task into the sequence to sequence translation task, where the input is a sequence of power distributions across the chip over time, and the output is a sequence of temperature distributions over time that looks somewhat like this. Now, if you can see this, this is something an AI model can easily capture. If you go back, right, a simple convolutional neural network can capture. And that's why the core architecture here we used is a simple encoder to decoder network with LSTMs into picture. And the LSTMs actually capture the time varying dependencies of this power distributions and the temperature distributions. And the encoder takes these power maps, and then the decoder generates the corresponding temperature maps at different frames. So we generated a lot of training data of this kind, of input power maps and ground truth temperature distributions. In fact, this was a work that was done in 2021 with collaboration at Qualcomm, where they had access to several different industry scale chip like power maps, and they gave us the corresponding ground truth temperature maps for using a commercial tool solver, ISPAC, ANSYS ISPAC. We collected that and we trained this large language, I mean, sorry, not a large language model, but this LSTM model to perform those tasks. And conventionally, the task which took over 3 hours to go from this power map to this ground truth temperature map, it could be done in a few milliseconds through a fast machine learning inference. You'll notice that the contours of this predicted temperature follow that of this ground truth temperature very similarly. Okay, so we brought down those hours of runtimes down to a few milliseconds using this sequence to sequence translation task and using this LSTM model. We've applied the same thing for IR drop prediction. This is for temperature prediction, but we've done the same for IR drop prediction. This was work that was done at NVIDIA when I was interning there on their specific designs. I encourage, if you're interested, I encourage you to take a look at this paper on how we used this idea of image segmentation or unit to perform IR drop prediction. Okay, so that was about analysis. And my third and the final topic here is going to be a short one on uh, whenever we talk about, AI and EDA, there's always this meta level question or this big picture question. Where did we get the data from? For instance, for this particular task, where did we get all these power maps from? In this case, we got it from Qualcomm, but how does Qualcomm give us thousands of different power maps to perform to train an AI model? Because we use 1,000 different power maps. Qualcomm did give us like 5 or 6. They didn't give us 1,000. So that is a bigger picture question here, that where did the data come from, right? When we're using AI in chip design. So if you think, so the idea here, what we present is to generate a lot of data to be able to train these models for AI in chip design. If you think about AI in chip design, if you think about AI itself, a lot of advances in AI, not AI in chip design, but the general area of AI, is because of advances, because of large amounts of data that's available, and because of the ability of compute today to be able to support large AI applications. That is the fundamental two reasons why we've had a lot of success in AI. But if you think about AI in chip design, there's not a lot of data that's available. The data is primarily hiding behind non-disclosure agreements, behind IP. To solve, we really need to come together as a community to create such data sets. But here I'll talk about one example of where we've created data sets using AI. So the idea here is motivated by the success generative adversarial networks, or GANs, have found in generating large amounts of synthetic data or image data. For instance, GANs are really good at generating synthetic pictures of faces. These faces look very realistic, but they're not of a real person. The idea here is, can we leverage GANs to generate synthetic yet realistic looking pictures of power maps so that we can train power related AI and EDA problems, or the power maps of real layouts? They're all synthetic, but can we generate synthetic looking power maps that look realistic using generative adversarial networks, and the successes they have found in generating fake yet realistic looking pictures of faces that are shown here. So the challenge is fundamental. We have to train a GAN now, but to train the GAN, we need data. But if we didn't have data, how do we really train the GAN and solve this problem? So the idea is to use this notion of transfer learning and to leverage uh, similarity with another source data set that shares similar characteristic traits um, as our domain data set or our target data set of real circuit data. So if you think about it, what we thought of is that urban satellite images have very similar characteristic traits as chip layout. If you think about urban satellite images, you have building tops that could represent macros on the chip. You have Manhattan geometry road distribution networks. If you think about downtown of any urban city in the US, you'll see Manhattan geometries of roads that are crossing out each other. Those Manhattan geometries are very similar to the Manhattan geometries of wires that are used in today's chips. So you can map these road networks as macro channels between the macros and wires within the chip. You can map uh, hotspots. There are a few amount of hotspots on the chip, and there are a few trees in urban satellite images. So you can map trees onto hotspots. And what you'll see here is an analogy between urban satellite images and actual chip layout that are shown here. So the idea was, can we take these urban satellite images, first pre-train a GAN model, and then perform fine tuning using real circuit data or real power maps to be able to make that GAN generate a large number of synthetic yet realistic looking pictures of images. And that idea actually turned out to be true, where we took a large amount of urban satellite images, trained this GAN here, took real circuit data, real power maps. We had about 5 to 6 that were available from Qualcomm, fine-tuned that data, that model using the real circuit data to be able to generate multiple fake yet realistic looking images of power maps that are shown here. We generated two categories of power maps, one without macros that are shown on the left, and one with macros that are shown on the right. And these images share very similar characteristic traits with real circuit power maps that were available. These about thousands of such power maps that are synthetically generated are available to the community to use on this particular GitHub repo. And And using these data points, we've run several different ICCAD contests on IR drop predictions, machine learning for IR drop prediction, and this to drive AI for EDA in this power-related aspect space. So that's about the end of my talk. So to conclude, I presented 3 different examples of how AI can help develop chatbots and improve productivity and lower the barriers to entry for a non-expert EDA tool user. I presented how AI can help speed up analysis. And I also presented how AI can help generate different data sets or synthetic yet realistic looking data for AI and EDA applications. AI has great potential to lower the barriers to entry and push the boundaries of EDA to help sort of do equivalent scaling and bridge those gaps that I talked about in the earlier slide, the gap that AI has created and the designer productivity gap. This is some future work that our group is looking at. We're trying to develop a complete comprehensive chatbot for open source chip design with RISC-V processors, with open source EDA tools and complete natural language-based chip design. We're also trying to extend the data generation aspects into generating synthetic netlists, synthetic layouts to train different AI models using AI. And yep, that concludes my talk. And thank you for your attention. I'll be very happy to take questions.
Thank you very much. So I have several questions, but I think first some student already posed some questions in the chat box.
Sure. So the chat box, let me bring that up. Okay, what kind of tools does OpenRoad generate scripts for? So OpenRoad is a tool in itself. OpenRoad is a physical design tool, and it performs different tasks such as, let me go back there. It performs different tasks such as placement and routing. Let me go back. Yeah, so this is OpenRoad. OpenRoad does this. There is no AI in OpenRoad, but we have built a chatbot to help a user use OpenRoad, if that makes sense. So it generates scripts to perform floor planning, placement, get the timing numbers. I am a designer. I want to query different information from the database. I want to change different information in the database. It can generate scripts to do that within OpenRoad. There's a question, can you use the same model and the methodology for designing microcontrollers as well? Can I ask a little bit more clarification on that question? Are we talking about which particular part of the topic are we talking about here?
Hello, am I audible?
Hi. Yes, you are.
Yes, actually, the tool that you described, it is basically used for the chip design purpose. Same way, rather than we have multiple chips on a single board, so can we use the same system for analysis of the whole board?
Of the whole board. So this is a ASIC flow right here, right now. This particular OpenRoad is for ASIC. So it's very specific to chip. It's not specific to PCB board or a larger thing. It's ASIC flow. So if you had a tool per se that could do that for you and you want to apply LLMs for PCB or package level stuff, sure, you can use the same methodology. But yeah, I don't know how that would work.
Okay. Thank you.
Yeah.
Thank you very much.
What motivated the use of urban satellite images instead of photographs of existing chips? Photographs of existing chips are very, very hard to come by. There are underlying microscopic photographs. Maybe you'll get manually, you'll be able to get hundreds, in the order of hundreds. If I go and I start mining, different websites and saying, okay, this is what a photograph of an existing processor looks like. That's not very widely available. Requires significant amount of effort. But to get urban satellite images, I just had to open Google Maps, if that helps. Yes, the difference is the abundance of data. That's right, Brian. Okay, so can LLMs also help optimize or analyze hardware design as well? Of course, that's where we're looking at. Right now, we've used LLMs primarily just for automation, but I think that LLMs or these mixture of expert models, right, where you get them for or multimodal models, not really large language models. I'll call it as a large circuit model. The concept is still the same, like a large language model, but I'll call it as a large circuit model. In addition to language, you can give it different inputs in the form of images. You'll notice here I've mapped the circuit to an image. You can map circuit to a graph. I didn't talk about that. That's an optimization. You can map circuit to a graph. So you can represent EDA data in different formats, as graphs, as images, as text, as language. So given that you can represent EDA data in all these three formats, we can sort of train this notion of what I call as a large circuit model. And that has potential in doing optimization. But this is what I think so. It's all skeptical. I mean, it's all skepticism now. I'm just projecting. I mean, I'm just trying to envision what's going to happen in the future in AI for EDA or AI for physical design. But I do see that as a next sort of where we're going. And it's where what our group is also trying to do. Can we get the presentation slide? Yes, sure. Happy to. Yep.
Is there some other questions from the audience? Yeah. So actually, I have some questions.
Sure.
And my first question is that we have some slides about like to use the STM to perform the prediction, right?
Correct.
Yeah. So I was wondering, whether you consider about whether we can further go one more step that to integrate those the domain knowledge, because we know that in the physical design we have a lot of historically has established a lot of the numerical models there. Whether we can further integrate those the data-driven method together with those the model-based method together to have better prediction or the estimation.
Yeah, definitely. So this one here is data driven, right? We fed a lot of data into this large language model. We gave it about, I think it was in the order of 1,000 data points, where we actually ran simulations for different 1,000 maps, generated the temperature maps, fed that into the model, and then trained the model, then performed inference, right? So is that what you mean by data driven, Bo?
Yeah, data driven.
So that's what we did with data driven. And the question was, can we use a combination of data driven and what was the other model?
Yeah, you can kind of integrate the domain knowledge there.
Correct. Yeah, so I've seen a lot of work that have tried to integrate the domain knowledge into the loss function, because you know that you're solving physical equations, right? So there's this concept called as PINS, physical neural, I forget what it's called. Physics informed, PINS, PINN, physics informed neural networks, where they try to incorporate the fact that, hey, you're fundamentally solving partial differential equations into the loss function and train it to solve that. So I think we can do a combination of both data-driven and physics-informed neural networks. That might be an interesting sort of, way it can go forward, and could be. I'm sure there are works out there that have done that. This was before PINNs came into place. This was mid of 2020 when we were working on this.
Okay, and another question is about it's kind of more open question. So you said that it's quite difficult to collect sufficient data, like especially chip data, right, from the
Correct.
industry. So instead, you use those the satellite map to kind of the surrogate.
Yep.
That, yeah. So I was wondering, do you think that is there any kind of the possible opportunity that the community work together that to form kind of the a better data set that everyone can share, can access, or to coordinate with the industry companies that to enlarge the existing data set?
Oh, yes. Oh, boy, you read I mean, that's something that we've been working on for a long, long time. So there are a lot of efforts that are coming, a lot of NSF targeted programs to try to just collect data, essentially. A lot of encouragement, typically the community never accepted data set papers, but AI has set precedent on the importance of data set paper just by the ImageNet data set. So you'll notice a lot of conferences such as DAC and ICCAD, and there's another conference, MLCAD, another conference called as LAD, Large Language Model Aided Design. All of these now are encouraging data set papers, or at least will not reject you outright, saying that there's no novelty, saying that there's no novelty. So that sort of encourages the academic community, at least to put out their data out there. And it really requires, as you said, the industry to come together and academia to come together. If the industry can release, some kind of meta level data, what do I mean by meta level? Data that is not proprietary to them, but they can release it. Like, hey, this is approximately, we have these many timing paths in our design. We have 1 million instances. The number of sequential cells in our design is so much. The number of combinational cells in our design is so much. Can you go and create a fake netlist that sort of, that's a proxy or a surrogate to our netlist with some sort of realistic characteristics? If the industry can help define what that proxy should look like, I think it can overcome that barrier of I can't release my data, but you don't have data issue. So
Okay.
yeah, so I think proxies is the way to go. We've talked, yeah.
Based on your interaction with the industry, do you think they have kind of sufficient interest to share their data?
Yes, they do have sufficient, at least not the big companies. I'm actually working with a smaller company and they are ready to provide metadata to some extent. And I'm trying to use that metadata to create more such fake data, synthetic data. It's still synthetic, but it shares, at least I know what the benchmark or how realistic this synthetic data is. And that realism comes from the industry. But beyond that, apart from one or two small groups that I work very closely with, it's very, very difficult. Industry will say lawyers are coming into play, and I don't know how to deal with lawyers, and they always say that, and that's a big challenge, and it's been a big challenge for decades now, Bo. But I feel like I'm optimistic things might get better, at least with the whole open source movement, RISC-V, the availability of some more designs in open source chip design world. So yeah, I think we have to work together with industry in defining what that proxy is or how a proxy is, and then that's the way we can go about it.
So in addition to that, if we think kind of more broadly or generally, so in order to to push forward such kind of effort, do you think that like so which actions that the community should kind of care about that? So whether like we need to establish some kind of data sharing standard and some policy, and whether there's some kind of more specific tools that can to help to automate such kind of data collections, and maybe
Exactly.
for example, yeah, for
Yeah.
example, the company they may provide some like a chip, and then but then they don't want to send engineers to specifically work on that, right? So whether we can kind of to provide such tool to facilitate their data collection procedure or something like that.
Yes, I 100% agree. The first part of your question was about standards. Um, in fact, I'm chair of the IEEE DATC committee. I mean, IEEE CEDA DATC committee. It's Design Automation Technical Committee. And one of our biggest goals is to try to help establish standards. If you notice, if you look at ICCAD, there's this contest on collecting data, essentially collecting data to train a large language model to dump out RTL code. So can we give a lot of Verilog code to an LLM, train it so that it can generate its own Verilog code for different tasks? Now that competition is run by Georgia Tech and NVIDIA together, and they've tried to get a lot of contestants to take part. I think they had about 70 contestants take part to just get data. Now, all of this data is curated, hopefully open source available soon. But there's an issue about standard that's come in now. How do you ensure that the quality of Verilog code that's
Yeah,
contributed by different people is of standard? If this Verilog code doesn't go through synthesis, if it has non-synthesizable constructs, if this
yeah.
Verilog code ends up with some sort of a race condition post synthesis, or it doesn't go down to tape out, it's kind of useless. Um, so there has to be some kind of automated way of checking whether the contributed data point is of quality. Whether if it's for the Verilog example, well, it's simple. You take all of that, you run, you run synthesis, you run functional verification, and okay, you can go ahead. But how many of those things do we run? Do we run it for all of them? How do we know what's the criteria? That's for Verilog. But for other data like chip layout data, how do you know whether this data is clean, DRC clean, or is it LVS correct? Is it doing the job that it's supposed to do? So it is a big standard. There are a lot of efforts from the community that are trying to address these standards. I mean, they're trying to address this concern about quality, policy, governance in establishing correct, good data sets. There's an effort that I'm a part of that's called SLICE. It's about creating infrastructure for this. There's a workshop, in fact, at NYU right after ICCAD on called ImageNets for EDA. So there are efforts, but let's see. Hopefully, something comes out of it that's very, very substantial.
Yeah. So actually, after listening to your talk, I was wondering, it's a very, very naive idea. I was wondering whether it is possible that first we have some kind of the experts that to generate kind of very standard script, and then we have very powerful machines that can automatically to perform from the Verilog writing to the final layout, and then we can repeatedly to do that. Then you can generate kind of very high standard
Data.
design examples.
Yep.
Yeah.
Yep. Question is, how much data, how many machines, how do you make that feasible, right? So
Yeah.
huge.
I think the first question is how many data do we
data
need?
you need.
Right.
Yep. And the thing with chip design is that data is so different. You need, like, the way a GPU looks very different from a CPU, looks very different from a RISC-V core, looks very different from an accelerator. How many of each category, how many of each class, how many of, if I train my model on this accelerator design, will that model work for a GPU? If I train my model, will it work for the CPU? So it's diversity, how much, quantity, quality, all of that. Yes, is big challenges.
Yeah, that's right. Yeah.
Yeah, so if we had a machine that could, in principle, like, just keep running, get Verilog code, generate Verilog code, take it out to tape out, generate Verilog code, take it out to tape out. Yeah. I think the problem is once somebody has to write that Verilog. So right now we're trying to use large language models to do it for us, but it's not very good right now. So
Yeah. I think seems that we still heavily rely on the kind of help from the industry.
Industry and manual intervention to a big part. We need experts to write, to check, to analyze. Yep.
Yeah. So any other questions from the audience? Okay, so if no more questions, so let's thank our speaker again. So yeah, thank you so much for a very good talk.
Sure. Thank you, everyone. It was a pleasure to be here. Thanks, Bo, for the invitation.
Okay, thank you. See you next week.
See you. Bye-bye.
Okay. So our next seminar talk will be the next week, still the next Thursday. Okay. See you everyone. Bye.